Hello, my name is Martin Langhammer. I'm the architect of the Stratix 10NX device, and on behalf of my co-authors, I'll be presenting today. The Stratix 10NX is the first FPGA specifically optimized for AI acceleration. Although this presentation is based on the paper, it's not going to be the paper verbatim. I'll be concentrating on aspects of AI FPGA architecture that are perhaps not immediately obvious. Today, I'll be focusing on bandwidth. The NX device is based on the existing Stratix 10 family. It takes a lot of time and money to develop a new FPGA architecture, so we can reuse an existing architecture, so much the better. This device is built on the mature Intel 14nm FinFET process, so that gives us good confidence in yield and performance. The AI Tensor Block is what makes the NX an AI device. There's about 4,000 of these blocks on board, offering up to about 500,000 embedded AI low precision arithmetic operators. 96 transceivers gives us a lot of bandwidth on and off the device. That lets us build data center scale systems if we want. In addition to the 7,000 embedded memories, there's 1 or 2 stacks of HBM2 that lets us store large models on board. If we have a look inside the device, we can see that the AI tensor blocks are organized in columns. Cascaded super blocks can be implemented, up to 33 blocks in a single column, continuously arranged. The columns of the AI tensor blocks are surrounded by other resources. There's memory, there's logic, and we can combine these all to build soft or mixed hard-soft additional functions that we commonly use for AI operations, such as activation functions. And these are explained in the paper. There's about 700,000 ALMs. These are the fractionable sixlets that can support up to 2 bits of arithmetic per ALM. So we have a lot of additional arithmetic capability, for example, for building the activation functions. So let's have a look inside the tensor block. There's 30 INT8 multipliers. They're arranged in 3 columns of 10 multipliers each. We can also decompose these into columns of 20 INT4 multipliers, in other words, 60 INT4 multipliers per AI tensor block. There's an optional shared exponent. This lets us build block floating point formats or shared block floating point formats, and these are explained further in the paper. Each column is a dot product and can give you a INT32 or FP32 output. Every column has an adder associated with it that's either INT32 or IEEE 754 single precision or FP32 format. We can use these adders to build the super blocks, to cascade all the blocks together, or at any point for a single block or for a super block, we can build an accumulator, either in INT32 or FP32. And there's various ways of getting that data out into the global routing. So we've had a look inside the block, and now we can start thinking about some of the bigger pictures. Just think about the FPGA as an iceberg. The resources are, the logic and DSP resources, the AI tensor blocks in this case, are easily visible. But underneath the surface is the routing, and the routing is what makes the FPGA the FPGA. The FPGA routing is both its greatest asset and its biggest liability. So we're going to be looking at the limitations of the routing and how we need to work with that to make all these multipliers accessible. FPGAs, especially the NX device, has a lot of bandwidth. There are 1 or 2 stacks of HBM that gives us 256 gigabytes per second per HBM. There's 96 transceivers that gives us a lot of connectivity on and off the board. If we look at each embedded memory, we've got up to 40 inputs and 40 outputs. That gives us up to 35 terabytes per second. The 4,000 or so AI tensor blocks have 80 bits of input data and 72 bits of output data. In addition, there's 28 additional bits of input data. That's used for signaling, control, and also loading the coefficients. Typically, what we're going to be doing is using the 80 bits of input data, but not a lot of the output data. We're going to be aggregating these blocks together in these super blocks in these columns. But still, we're going to have to find 20 or so terabytes per second to feed all the multipliers. And what we're going to see here is that we don't have enough routing. No FPGA will have enough routing for this, so we have to find a different way around it. So bandwidth everywhere means wires everywhere, and we don't have enough wires. If we look at this FPGA in INT8 or block floating point 16 mode, we've got about 120,000 multipliers. Those will need about 2 million wires, and we're going to need to get those 2 million bits to all these multipliers in every clock cycle. We only have about 300,000 or so wires to the AI tensor blocks data wires. In fact, there's additional wires used for coefficient loading and control. So we've been working on FPGAs. The industry's been working on FPGAs for the last 3 or 4 decades. There's only so many wires that we can get on board. Remember from the iceberg that the routing is the biggest limitation. We're not going to be able to put 6 times as much routing on board just to feed the AI tensor blocks. So what do? Well, for AI processing, we can take advantage of the typical access patterns that we're going to find for the small matrix or matrix vector operators. And by preloading the weights in one dimension and streaming the data or activations through the other dimension, we're able to pretty well get 100% utilization out of our device. We call this virtual bandwidth expansion. An important part of virtual bandwidth expansion is loading the weights. So we've got 3 different ways of loading the weights. We've got to get those in on the one dimension before we can stream data through. We've got a very wide pipe. This allows us to load the AI tensor block in 1 to 3 cycles. The problem is during those 1 to 3 cycles, the AI tensor block cannot operate. There's a narrow pipe method. Over 15 to 18 cycles, we can load the weights in, or the next set of weights in. There's a dual bank of weights, so we can load the one set of weights in while the block continues to process. There's also a very thin pipe. This is based on the super block format. The advantage of this method, even though it takes a lot longer to reload the weights, is that it really reduces the wire load into the super column, which makes the fitting a lot easier. While the AI or the tensor mode is the mode we want to operate in most time, it allows us to get the maximum performance out of the device. We can't use it everywhere. And sometimes we'll need to use a vector or scalar mode. So the vector mode allows us to build a small dot product. This is going to be 5 or 6 multipliers, depending if we use the optional shared exponent. The advantage of the vector mode is that we can change both inputs into all the multipliers at the same time. Occasionally, we need access to individual multipliers or adders. And for this, we can use the scalar mode. Now, we can use the multipliers, adders, or both in these modes. And one thing that should be obvious here is that the more flexibility we want from the block, the less performance we're going to be able to get out of it. Now, those numbers I showed you earlier about the bandwidth were at a nominal 500 megahertz, and we want to, our desire is to run this device at 500 megahertz. We think that this is the right operating point for this device. To prove this, we've created two test cases for the which are detailed in the paper. One is the pathological test case. This is going to be sort of unrealistic, or is the type of design that's you don't really want to use. We've created two large buffers that feed the entire device. So we're using about 90% of the AI tensor blocks in both these cases. We're leaving about 10% reserved for things like building mixed hard-soft activation functions. The issue with this pathological test case is that we're going to have large, wide buses that will span the entire device. This is going to be a very difficult fitting problem for both the device and the tools. We're still able to meet about 400 megahertz for a mid-speed grade device with this design. A more representative test case is building a systolic array. The maximum route length is much lower. Again, we're using 90% of the AI tensor blocks, and we're able to achieve over 500 megahertz. Now, both of these are for mid-speed grade devices. If we recompile for the fastest speed grade device, will be over 600 megahertz. Important thing about both these designs is, and this is detailed in the paper, is that the wire load is very high, as we expect, but it's only high in one direction. The opposite direction, the wire load is very low. So this means that by doing a bit of floor planning, that even if you use all the resources in the device, and I mean the ones that are not used for this, for example, all the logic, as quite a bit of the logic is reserved, we should still be able to achieve about 500 megahertz for a realistic systolic network in this device in a mid-speed grade. So in conclusion, there are never enough wires. There are never enough wires in the regular FPGA world. There's certainly not enough wires in the NX part, but by using virtual bandwidth expansion, we're able to extract all the performance out of the device. Thank you.